All right, section 8.6, we're going to get into some really interesting stuff with manipulating a function to turn it into a series. So we're going to learn how to represent functions as a sum of power series by manipulating a geometric series, or we could even differentiate or integrate something like that. And the question you might be thinking right now is, why on earth would we ever want to change a function to a series? Because series are awful, right? Well, actually, a function written as a series makes it a little bit easier for calculators, computers, and those things to understand. Also, it helps you to integrate functions that don't have easy antiderivatives. It helps you solve differential equations. So there's actually a lot of application of this skill beyond what we're just going to learn today. So I want to point out a couple things to you, okay? If I said to write a few terms of the series x to the power of n, if we're starting with n equals 0, hopefully you guys would feel pretty comfortable plugging in 0, 1, 2, and so forth, right? Like you understand what a series is telling you to do. This would be also equivalent to a function, okay? And the function would be 1 plus x squared plus x to the third, growing infinitely large. This also happens to be a geometric function, right? This is geometric because we're multiplying by x each time. And because it's geometric, we can find the sum of the series. The sum of the series is always found by doing a over 1 minus r. And in this case, a is 1, first term. R is x, because you're multiplying by x each time. And so the sum of the geometric series and the terms of the geometric series are equal to each other. So we can make a conclusion that 1 over 1 minus x represents the sum of a geometric series, which also then represents 1 plus x squared plus x to the third plus everything and so forth. So basically, if I had 1 over 1 minus x and I needed to investigate that, like take an antiderivative or something, I could write it as a series and then antiderive this series. Okay, easier to antiderive the stuff on the right than it is the stuff on the left. The stuff on the left, by the way, you'd have to use partial fractions to antiderive that. So that's the whole point of this lesson, okay? So in example 1, we're going to get straight to it. We're going to say express 1 over 1 plus x squared as the sum of a power series and find the interval of convergence. Okay, so we're going to have to do kind of what we had back here in this first example, but in reverse a little bit. So we're going to first try to figure out what 1 over 1 plus x squared means as a geometric series. So your goal is you're going to try to make this look like the sum of a geometric series. And that means make it look like a over 1 minus r, because that's the sum of a geometric series, right? Okay, well, we're pretty close. We have a number on top. We have 1 plus something. So we need to just adjust right here. We need a minus. So I could very easily make that happen. I need to make sure I'm still algebraically equivalent, of course. If I just put a double negative, right? That would work. Now I'm in the correct format. And when I'm in the correct format, then I know that the top number is my a value. And I know that 1 minus whatever comes after that is the r value. So we can take these two things and we can turn it into a geometric series. We want the first term to be 1, right? And we want the ratio to be on the inside to the power of n. Does that make sense to you? So a is the first term, and then r goes inside here. So you just took a function and turned it into a series. You understand what you're doing? You took a function and turned it into a series. It's a pretty big deal. Now, the series could use a little work. Like the negative, I could pull that to the front and make it -1 to the n. And then maybe we could write it as x to the 2n. Does that make sense to you? X squared to the power of n, you would multiply the exponents, right? Okay, so we have a series. So then it says find the interval of convergence. Okay, though that shouldn't be too bad because that's what you did in section 8.5. So hopefully you remember that to find the interval of convergence, you're applying the ratio test. Okay, and you're using your series that you just created. So we're going to set this up. I don't know what I'm doing. Let's try again. Remember, you don't have any outer inner to do this time, but remember you do need to break things apart to try to simplify. What can we do? Well, the negatives will go away because we're doing an absolute value. We could make this x to the 2n plus 2, which let me go ahead and just break that up. That would be x to the 2n times x squared over x to the 2n, which now those are going to cancel. And this is kind of weird because there's no n's left. So when it says take the limit as n goes to infinity, you actually can't. That doesn't make any sense anymore because there are no more n's. So disregard the limit part. Remember that in order to converge, it needs to have a number less than 1. Make your interval. And then technically you would actually square root before you undo the absolute value. So your answer is just going to be -1 to 1 is your interval. Okay, let's try another one. Find a power series representation for 1 over x plus 2. Remember, power series is the same thing essentially as a geometric series. So you're just finding a geometric series for it, okay? So same goal. You have 1 over x plus 2. You need to make it look like a over 1 minus r. So the first thing I would do is I would say, okay, I actually need the number to be first. Oops, not a minus, that's a plus. And I really need this number down here to be a 1, and I have a 2. So what we can do is we can actually go through and divide the entire equation by 2. Expression, not equation. Divide the entire expression by 2. Okay, and then I need a minus, not a plus, which we've done that before. So we're just going to make it 1 minus -x over 2. So that does now look like a geometric sum. So we can turn that into a series. And remember, to turn it into a series, you're taking the first term, which is on the top, so 1/2, and then the common ratio, which is on the bottom, the -x over 2, and you need to the power of n to make it geometric. So we're calling it power series, same thing. I think we would probably be smart to break it up a little bit, mainly the negative. Actually, you know what? I see a couple things we can do. Hold that thought. Let's take the negative out. We can actually do this. Watch. I have 1/2 on the outside, right? But I could also write this as 1/2 to the power of n, meaning this like over 2 thing, x to the power of n. Then I could, just showing you like your options, okay? Then we could do a little bit more. Since these both have 2's on the bottom, with ones on the top, we really could just say, all right, instead of writing them as separate fractions, let's just write it as 2 times 2 to the power of n. And one more thing, you see how these are like bases? Couldn't we combine them by adding the exponents, right? So I think the best option we have here, best we can do, is this. Pretty good. Okay. Let's try another one. With these, there's just so many different ways they can look, so we're going to have to do a lot of practice to get this right. X to the third over x plus 2. We have to make it look like a over 1 minus r. Really, you just need to kind of focus on the fact that you can have whatever you want on the top, but you need a 1 minus right here. So I'm going to start with I need a 1, so I'm going to have to divide everything by 2. And then I'm going to have to change it to a minus, so I'm going to have a double negative. And I think I'm set. Now I have my value of A and my value of R, so let's turn it into a series. Okay, so we have A is x to the third over 2. R is negative x over 2 to the power of n. Okay, let's do some rearranging. I think it's going to be a lot like the last example. I have a negative 1 that I could move out, so negative 1 to the power of n. X to the third, the top would be x to the third, x to the n. You could write that as x to the n plus 3 or 3 plus n. And then the 2's on the bottom can be combined. This would be like 2 to the first and 2 to the n. So 2 to the n plus 1 would be the same thing. Oh, I wanted to show you a little trick. Just show you something that is possible, something you may see in the future. A lot of series start with 0 or 1. Technically, you can make a series start with any n value you want. Just takes a little bit of finagling. If you were, for some reason asked to change a series and say, instead of starting at 0, start it at 3, all you would have to do is kind of in your head think that you actually have 3 less terms than what you typically would have, because this starts at the 0 term, this one starts 3 terms later. So you would have 3 less terms. So that means you would have to subtract 3 from any of the n exponents to accommodate for that 3 less terms scenario. So that would mean you would have your exponents changing a bit. Negative 1 to the n minus 3 power. Remember, this could be anything like n minus 1, n plus 1. Any of those would fit here, since it's just negative 1. And then this would become x to the n over 2 to the n minus 2. So this would be equivalent statements.